Welcome back to Mechanical Systems Design. In this video, we're going to go over Project 3. We've been working through your reports, and we noticed some things where we had room for improving our understanding. So we wanted to go over these to solidify our knowledge heading into Project 4. The first thing to do is just to be sure to really lock in these two equations, the torque balance and the voltage balance. And in the torque balance, notice that the load torque is equal to the motor constant times the motor current minus the friction torque. So the output torque of the motor won't exactly equal Ki. We'll also lose some torque to friction so that the output will be a little bit less. And in the voltage balance, we have that the applied voltage is used up in two different ways, and they're both important. One is this electromechanical component of voltage, K theta dot, and the other is this ohmic voltage drop, where we have IR. And depending on the state of the motor, theta dot and I could both be substantial. So both of these terms usually contribute a lot to the voltage balance, and it's not a good idea to ignore either of them, usually. Now, if you ever feel unsure about those equations, one great way to get them is to, and you could go look in the topic reading course, but you could derive them for yourself. And all you need is this free body diagram of the motor rotor and this circuit diagram of the motor, where we have this resistance and electromechanical voltage drop. And, it takes a minute to do these things, but then you'll be sure that you've got your equation right. And the more times you go through these analyses, the faster they go, the more easily you can apply them to new domains, and the firmer you'll hold this knowledge, both intellectually and intuitively. All right, so let's talk about how we're going to use these equations for characterization. In general, what we want to do is first go through and identify which things are characteristics that will be constant always, which things are going to depend on the state, and so on, which things we can measure, and then try to find the easiest thing to characterize and do that first. So let's look at these equations again. In the first, we have this load torque. That is the output torque of the motor. It's going to depend on the circumstances, right? If we connect this to some big, a gearbox with a heavy load on its capstan, that will be high. If we let the motor free spin, it will be 0. So this is something that we can't characterize. It's not a property of the motor. It's part of how the motor is interacting with the rest of the system. The motor constant, you'll remember, is a characteristic of the motor. That has to do with the geometry of the coil and the strength of the magnetic field. And that will always be true for our motor, no matter how fast it's spinning. Current, that will be, again, state dependent, and it's something we can measure just by looking at the current reading on our power supply. Torque, the friction torque, that will also be a characteristic of the motor that's going to arise from this friction between the brushes and the commutator inside the motor. Applied voltage, that's something we get to choose, and we'll know what it is from the power supply. The motor constant, same motor constant. There's just one because they're both dependent on exactly the same geometry and field strength. The velocity of the motor, that's something we're going to be able to measure, either by measuring it on the motor directly if we have some very high-speed tools, or by measuring the velocity of the output of the gearbox and knowing that the velocity of the motor is exactly the gear ratio times the velocity of the gearbox output, because the teeth can't slip. We have this coil resistance. That will be a characteristic of the motor. It just has to do with the material in the coil and how long it is and its diameter. And then again, current, which we already know we can measure. So we know that we want to estimate the motor constant, the friction torque, and the coil resistance. The easiest one to get out of these, it will turn out, is that we can try for each and notice that, oh, I wish I had this other information. And if we do that for kind of all three, we should see that the coil resistance is the easiest to get. And the reason is you can remove this term this electromechanical voltage drop by keeping the motor from spinning, setting the velocity to 0. So you stall the motor, you grab the output, and then there is no voltage drop due to movement of the coil, and all of the applied voltage goes to IR, goes to overcoming coil resistance. And so apply voltage, measure the current, divide applied voltage by current, and you get the resistance. To get the motor constant, if we look at this voltage balance equation again, we'll see that now we don't have multiple unknowns. So we've now characterized R, and so this just becomes some term we can calculate by measuring I and using our previously estimated value of R. And then for any applied voltage and any circumstances that the motor might be in, we can know what the applied voltage is from the power supply, measure the current from the power supply, and measure the speed, say by counting revolutions of the output of the gearbox or something, and calculate K. And should always be true, it should always work. The easiest way might be with no capstan on, because it makes it easier to see the, say, the spring pen or something like that. And you don't need to print a capstan to do that. And finally, we have the motor friction. So once we have the motor constant, then we can eliminate this load by not connecting the motor to anything, letting it free spin. And then we'll see that the friction torque is going to be equal to the motor constant times the measured current, as we derived in the topic reading. So that's how we can quickly characterize all of these motor constants for our motor. And if we do this at lots of different, say, values of applied load or speeds, and same thing here, speeds or applied voltages, equivalently in this case, we'll get a range of values. And the reason is because we'll have errors in our measurement, and our model is an imperfect representation of the real system. It's a close approximation, but it's not perfect. And so by taking lots of measurements, then we can reduce the effects of model error and measurement error on our estimates. And you can just average the calculated values. So the last thing we're going to try to calculate is, or estimate for our system, is the gearbox efficiency. And we're also going to use efficiency thinking for some of our calculations later. So let's really dig in on this from a high level. And so the first thing to remember is that the efficiency is the power out of the system divided by the power in. So you're going to pay some useful power into the thing, you're going to get some useful power out, and you're going to lose some power to, say, heat because of friction or heating the coil or something like that. And so just the power out that's useful divided by the power in that's useful. For the motor, the power out will be mechanical, and it will be the torque of the motor, that load torque, times the velocity of the motor. And this is an equivalent translation would be force times linear velocity, and it's this is work divided by time. For the power into the motor, we have the applied voltage times the current. And one way to remember this is that the applied voltage is like a force or torque. It's trying to push the electrons through the circuit. And the current is like a velocity. It's like how fast the electrons are moving through the circuit. Now, something to remember is that the efficiency of the motor is not a property of the motor. It is not a constant characteristic of the motor. It depends on the motor operating point. So if we change the voltage or we change the speed at which the motor is operating, the efficiency will change. And that's true even if there's no friction. So this dashed line here, remember, is for an idealized motor that has no friction. And we can see that if the motor is spinning very slowly, the efficiency is very low and it reaches 0 when we stall the motor. That is, the motor uses a lot of electricity, but it puts out no mechanical power. In this idealized case, it can approach 1 in this really weird edge case. But even like in the middle here, where we're at, say, half of the no load speed at that peak power point, we're getting only 50% efficiency with no motor friction. And the reason that you're losing energy there is because we're heating the coil. So that IR term is causing a voltage drop that's not going towards this electromechanical component of voltage, and the power that's going into that is the voltage drop over the coil resistance times the current through the coil resistance. So that will be IR times I, so it's I squared R. And that is the primary contributor to energy loss in the motor and inefficiency. You'll notice if we add some friction, here we've added 10% of the stall torque as friction, then the efficiency does drop off of the ideal case, but still most of the loss here is to that ohmic resistance of the coil. All right, so we want to characterize the efficiency of our gearbox as well, and that is going to follow the same thing. We'll have the efficiency of the gearbox is the power out divided by the power in. But note that the power out will be, both of these powers will be mechanical. The power out will be the torque out times the output velocity. And the input will be the input torque times the velocity of the input, which is just equal to that output velocity times the gear ratio. And the output velocities will cancel, and we'll have that the output torque divided by the gear ratio times input torque is the efficiency for our gearbox. And another way to think about this is that all of the energy loss in our gearbox is due to friction. It's not due to velocity loss. There's no slipping of teeth. So what's happening is friction resists rotation of the gears. And so the ratio of the actual torque out to the ideal torque out, if we didn't have any friction, is the efficiency. Another thing to remember about the gearbox is that the efficiencies of each stage multiply. And the reason that that happens is because that power out is equal to the power in times the efficiency, right? So let's say we had 2 stages in our gearbox, and each has an efficiency of 50%. If I put in 1 joule into the first stage, out comes half a joule. That half a joule is what's going to go into the next stage. So the next stage gets half a joule in, and out comes a quarter of a joule. So for the whole system, I put in 1 joule, I got out 1/4 joule. So my efficiency is 1/4, or 25%, and that's 50% times 50%. If I added them together, or said that the total efficiency was 2 times 50%, then I would get 100% efficiency. And I would expect to put in 1 joule and get out 1 joule. But that doesn't make sense, right? Adding more energy loss sources shouldn't increase the efficiency of the system. And you can sort of see this also by calculating in the math, the torque out of the first gear stage is equal to the torque into the next gear stage. So these things will cancel. And if we multiply it out, the total gear ratio is equal to the multiplication of each gear stage ratio. And we derived that in the topic rating on gears. So the net effect is if each of our gear stages has the same efficiency, then the total gear efficiency will be the stage efficiency raised to the power of the number of stages, and not multiplied by the number of stages, say. Now, how do we characterize overall efficiency experimentally? Well, the way to do it is to apply a known output torque, say by hanging a weight of known mass off of your capstan of known radius, and then measuring what is the input torque from the motor. And the way you get at that is from that torque balance. We have that this input torque from the motor, that'll be the load torque. It's just going to be Ki, I we measure, K we've characterized, minus tau fric, which we've already characterized. And if we did this for a few different values of output torque, measuring I and calculating what the load torque is in each case, we get a few different estimates for the overall gear efficiency, and we could average them to get a robust estimate. As we do those kinds of things, it's important to do that near the expected operating conditions. So if we say expect that our motor is always going to, when we use it for our task, it's going to be spinning around, I don't know, 1,000 radians per second, but we always characterize it at 100 radians per second or 10 radians per second. Well, some of the things we calculate probably won't be very accurate. The errors in our model will start to really show. Similarly, we wouldn't want to say, expect to operate our gearbox with an output torque of 1 Newton meter, but do all our tests at 10 Newton meters. So whenever possible, you'd like to cover the range of possible operating points and sample it relatively evenly. It gives you a more robust experiment. Okay, so now we've characterized everything. How do we pick our set point? Well, one choice we have to make is the voltage. Now, if we step back and think about what the task is mechanically, we'll see we have to do a certain amount of work. We're trying to minimize the amount of time over which we do it. And power is work over time. So if our time gets smaller, our power gets higher. So we're really trying to maximize power output. And power is proportional to voltage squared. So we want to choose the maximum voltage that we can. In this case, it was 6 volts. And then later we'll want to check things like, will my motor overheat if I do that? The other thing in our set point is how fast are we spinning the motor? And that's going to affect the power as well. Now note that if we want to maximize the task speed, that does not mean maximizing the motor speed. If we increase the motor speed to, say, it's no load speed, our power will go to 0. And so we really want the speed that corresponds to the maximum power approximately in this task. More power, that'll give us a faster lift. And but what about the gearbox? Well, remember the efficiency of the gearbox is the power out divided by the power in. More power in leads to more power out generally. So how would we make that happen? Well, we have the choice of our gear ratio and capstan. So we know that the output torque from the gearbox will be the mass, the payload mass times gravity, that gives us a force, times the radius of the capstan, that gives us a moment, torque. And then the motor will experience a load that is proportional to that, modulated by 1 over the gear ratio and 1 over the efficiency of the gearbox. I've already characterized this for a given number of stages, so we know what that's going to be. And we get to choose this, and we get to choose this. So what we really want is to pick R cap over RG such that, we get the desired T load, or you could rearrange this equation and solve for R cap over RG. And then there's lots of different values of R cap and RG that would give us that. So you could say guess at RG and then solve for what R cap is. Or you could notice that fewer gear stages tend to result in higher efficiency. And so you might try to get RG to be as small as possible. Since we want R cap over RG to be some value, that would mean making the capstan radius as small as possible as well. And if you used a more complex model of the system, maybe you separately considered friction between the output shaft of the gearbox and the housing of the gearbox, then the efficiency approximation doesn't quite hold, and there's slightly different mathematics. And a straightforward way to address that case would be just brute force optimization. Have nested for loops and try every allowable gear ratio and a wide range of plausible capstan radii, and then see if you've got those two things and you know this efficiency. If you know the gear ratio, then you know how many stages and the total efficiency, G and M. That'll give you the load torque. If you know the load torque, you'll know what the current is, because the load torque plus friction divided by the motor constant, that's the current that the motor must experience. If you know the current, then you can go to your voltage balance equation and solve for the speed of the motor. And then you have your gear ratio, so divide the motor speed by the gear ratio, you get the capstan speed. And then you can solve for how fast the payload is lifted. And you can do that for every possible combination of R cap and RG, if you had a more complicated model. Now, something we notice is that several people overheated their motors. And There's a couple of good pages on this in the topic reading on motors that are worth a look. Basically, there are a couple of ways you could try to avoid this. One is a conservative approach. And the thing to understand here is that at steady state, the power flowing into the motor from your power supply, or really from heating of the coil through joule heating of the coil, should equal the power flowing out because of heat transfer to the environment. And so, the temperature difference between your motor at steady state and the environment should equal the coil resistance times the thermal resistance times I squared motor. And we talked about how I squared R is the power flowing into the motor flow. So if you make sure that the square of the current going through your motor never exceeds this value, it's impossible to overheat your motor. But that is conservative, right? If you know that you're only going to run your motor for a certain amount of time, you might be able to put more energy into the motor before it reaches its overheating temperature. And the temperature of the motor will be, in time, will follow this equation where we have the temperature of the motor is a constant here. This is the steady state temperature of the motor if we let it go for indefinitely. And another constant, including initial temperature, times the exponential of 1 over this time constant. Time constant is sort of how fast the system changes temperature. It is the thermal capacitance of the motor times the thermal resistance of the motor. So if there's more heat storage inside the motor, it will change temperature slower. And if there's more resistance to the heat leaving the motor, then it will change temperature more slowly also. And if we rearrange these terms and solve, we'll find that there's some allowable current over some time, starting from some initial condition. And so if you want to be aggressive and you know you're only going to run the motor for a brief period of time, this value of the allowable current will be a lot higher. Now let me give you an example of this for our motor based on the thermal constants that are provided in the project description and topic reading. So here we have the maximum allowable temperature, that's 50 degrees Celsius. And this blue line is the actual, our estimated temperature of the motor when we pulse it with, we stall it, we pulse the temperature by stalling it and applying 6 volts for 20 seconds. And you can see the temperature just shoots up. We're putting a lot of energy into the motor during that phase. It might not seem like a lot because there's just this power supply, you plug it in the wall. But if you think about it, given the values of R, the power going into the motor is around 50 watts. Yeah, for 20 seconds, it's about 1,000 joules. 1,000 joules is a lot of energy, a kilojoule. That's about the same as if you took a 100 kilogram weight and drop it a whole meter. And so we can easily kind of really put a ton of energy into these systems very quickly. It's a little deceptive. And then if we turn off, we disconnect the leads using the alligator clips very quickly, then the motor will take a long time to cool off. This is about a little shy of an hour. If we instead waited, say, 10 minutes and then plug it back in, install it for 20 seconds again, we're going to exceed the maximum sustainable temperature and burn up a motor. So keep an eye on this for Project 4. So if any of this stuff felt still unfamiliar or confused about it, this is a really good time to dig in and really get to understand it because we're going to need it for Project 4. So you can go back and reread the topic readings or rewatch the topic videos or talk it over with your the lead of your coaching group. All right, good luck in Project 4.